Right, question 12. It's quite a nice question, quite a nice one that combines both projectiles and energy. So let's have a look at this. So we've got a fountain. We've got a garden pond contains a fountain. The water's been pumped and ejected into the air, and it's going to follow a parabolic curve, isn't it? So gets us thinking about efficiency first, which is nice. Show that the water leaves the nozzle at a speed of 8 meters per second. So it's all about energy. If you see efficiency, you think energy, don't you? Okay, so let's have a little look at this. Right, now we've got power. We've been given values of power. The power in is 160 watts. That's the power of the pump. So the electrical energy is going in to the pump at a rate of 160 joules per second. So that's a good starting point. So power in is 160 watts. It's 76% efficient. So the power out, okay, the energy given to the water per second is 160 times 0.76. Now that is 121.6 joules. 121.6 joules per second. Watts, sorry. There you go. So that's the amount of energy given to the water per second. That's quite nice because it gives us the mass per second here, doesn't it? So what we need to do, like when we do momentum questions that involve water or fluids being moved, we think about what happens per second. Okay, we know the energy given per second, and we know the mass that's moved per second, so we can combine to say what's happening every second. It's as simple as that. So we have the energy per second is this. Now, there's something caught me out at first. We've got kinetic energy being given to the water. That's how we're going to find the speed. But it's also been given a little bit of GP as well, hasn't it? Okay, so because the water has to be pumped up through this height before it's ejected at 8 meters per second. Okay, so we're going to say, okay, this total energy per second, 121.6. Now, some of that is given as GPE per second. Now, per second, we're given the mass, aren't we? So 3.5 kilograms per second. So we have, let's write it out first. Actually, that'd be easy, wouldn't it? So we've got GPE per second plus kinetic energy per second. Okay, so 121.6 equals, right, let's do the gravitational. So we've got the mass per second, 3.5 times 9.81. The little height it goes up is 0.45. So that's a GP per second. That's added to, now the kinetic energy per second, we've got a half times the mass per second. Again, it's the same value, 3.5 kilograms every second, multiplied by v squared. There you have it. Okay, the only unknown there is v squared. So if we thrash that out, we get the velocity to come out as 7.78 meters per second. Okay, so always write that down. This is what the examiner wants to see. They need to see the true value. Don't write down v equals 8. Please do not write down v equals 8 because v is not equal to 8. It's suggesting that v is about 8 meters per second. The reason why they give you, they suggest a value is if you need this value for the next part of the question, which you do. Don't ever write down that as your answer, please. The answer is actually 7.78 meters per second squared. If you really want to annoy me, then please go ahead and say that that is roughly equal to 8 meters per second squared. I see this all the time from A-level students, and it drives me mental. Okay, I went to university. I studied physics. The examiners probably went to university and studied physics. They're very likely to have done some maths at university. They don't need to be told that this number is roughly equal to this number. So, no need, guys. No need. Right. You can see that that's roughly equal to 8, can't you? Anyway, going off topic. Right, here we go. Next part, B. Determine the horizontal distance. Right, it's suddenly turned into a projectiles question, which is nice. So, what do we do for every single projectile question we get thrown at us? Okay, we split it into horizontal and vertical, and we do the calculations separately. But before we do even that, we draw a cheeky little diagram. Okay, it would be really useful to be able to see, I think, the initial velocity. So it's ejected at 7.78, isn't it? Now the angle we're given is 25 to the vertical. So I'm going to say that's got to be 65 degrees, isn't it? Okay. Might help, might not. Might help to draw in the two components, the vertical and horizontal component. Obviously, the horizontal is 7.78 cos 65, and the vertical is 7.78 sine 65. But you knew that. Anyway, what do we do now? We split the space on the page in the question into two, because we're going to do, and we always do vertical first and then horizontal. This is what we do with every single projectiles calculation. Right, vertically, what do we know? We know the initial vertical velocity is, let's take upwards as positive, 7.78 sine 65 degrees. Right, we want the time, because we need to calculate the horizontal range here. So the water's going to do this, isn't it? It's going to go follow that path. Okay, it's going to follow a parabolic curve, and we want the horizontal range. Now we want the time it hits the level, the horizontal level of the starting point. Okay, so we hang on a minute. Need, so just pause in there for, yeah, I'm just checking that. There's the start point, isn't it? So the water is ejected. It's going to follow this parabolic curve. Now, because thankfully the lip here, or the edge of the pond. Okay, so yeah, we want this to be our final point for the water. So we're going to calculate from that the exact horizontal range that we have available to us. Okay, right. So back to the question. So what else do we know? Okay, my favorite way or my favorite equation, there's two equations of motion we can use here, but I much prefer using v equals u plus at, because we don't have a quadratic involved. Now the water, when it hits here, is going to have a vertical velocity of minus 7.78 sine 65, if we can ignore air resistance. Okay, now the acceleration, minus 9.81. Now the time we want to calculate. So what do we got? Substituting into for v equals u plus at, we have minus 7.78 sine 65 equals 7 0.78 sine 65. V equals U plus AT, so it's plus minus 9.81 T. And that comes out, when we calculate it, with a value of T to be 1.44 seconds. Okay, so now we know the time it takes for the water to do that and hit there. So, horizontal bit is more straightforward. This is where we're going to use V equals distance over time. Because the horizontal velocity doesn't change, because we're ignoring air resistance, we can get horizontal range is VT. So the horizontal range here is 7.78 cos 65, isn't it? So 7.78 cos 65 times 1.44 gives us a horizontal range of 4.74 meters. Okay, is that correct? Right, last bit of the question is about the air resistance. Okay, the last bit of the question. Okay, explain one of the reason. All right, this is an overestimate, because obviously in reality air resistance would slow down the water, so it would actually fall shorter than our calculated value of 4.74. But it wants to know another reason, any other reasons why it's going to fall short of 4.74. Well, we can't use air resistance because it's mentioned. The obvious other one is friction between the water and the pipes. Okay, whenever water flows down pipes, there is always friction between the molecules in the water that are in contact with the pipe. Okay, and even molecules of water that rub against each other also will exhibit friction, so it does slow down the water slightly, which will reduce the initial velocity of the water. Okay, hope that all made sense. Quite a nice question, that. I like that. Thank you.